We would like to derive the fundamental equation of thermodynamics, which tells us how the internal energy of a system changes if we change the entropy, volume, or number of particles. We will make the following assumptions. The top equation says the first law of thermodynamics is true. We assume that the change in internal energy can be due to heat flowing into the system or work done on the system. We assume that the internal energy is a state function, so that the change in internal energy doesn't depend on whether or not you take a reversible path or an irreversible path. It's the same for any path between the same initial and final states. We define the entropy to be change in entropy equals heat added to the system at constant or during a reversible process divided by the temperature. The work done during a reversible process is negative the pressure of the system times the change in volume. And the Gibbs free energy is defined as enthalpy minus temperature times entropy. The enthalpy is equal to the internal energy plus pressure times volume, and we define the chemical potential as the derivative of G with respect to particle number N at constant pressure and temperature. So write the first law of thermodynamics assuming that the number of particles does not change, so that the only way that you can change the internal energy of the system is by adding heat, dQ, or doing work on the system, dW. Since internal energy is a state function, it doesn't matter whether you take a reversible path or an irreversible path. So therefore, the first two lines are equal to each other. But if we take a reversible path, we can write the change in heat as TdS because of the definition of entropy, and we can write the change in work as negative P dV, so that the change in internal energy during a reversible process is TdS minus PdV. But of course, internal energy is a state function, so it doesn't matter whether or not you take a reversible path or an irreversible path. The change in internal energy is always going to be TdS minus PdV. But remember, we assume that the number of particles is constant. Now the definition of free energy, or Gibbs free energy, is H minus Ts. The definition of H is U plus PV. Take the differential of both sides. Use the product rule. Then we just proved that du is TdS minus PdV if we hold the number of particles fixed. So therefore, the change in Gibbs free energy is the fifth line, assuming that the number of particles is constant. Cancel the various terms that cancel, and we get that if the number of particles is fixed, the change in Gibbs free energy is V dP minus S dt. So rewrite this in orange. dG equals V dP minus S dt. And according to calculus, a small change or a differential in the Gibbs free energy can be written as the derivative of G with respect to P dP plus the derivative of G with respect to T dt. This assumes that the Gibbs free energy only depends on pressure and temperature and nothing else, which means, once again, we're holding the particle number fixed. So comparing the top equation with the middle equation, we see that the volume is the derivative of G with respect to P at constant T, and the negative entropy is the derivative of G with respect to T at constant P. Now, let's relax our assumption that the number of particles in the system is constant. If we relax that assumption, the Gibbs free energy is going to depend on the pressure, temperature, and the number of particles. So the chain rule says we have to write a small change in Gibbs free energy as a term due to a change in pressure plus a term due to a change in temperature plus a term due to a change in particle number. And we define the derivative of G with respect to N at constant pressure and temperature as the chemical potential mu. And we've already shown the derivative of G with respect to P is volume, and the derivative of G with respect to T is negative entropy. Now, we already know that the Gibbs free energy is H minus Ts, and we already know that H is U plus PV. On the third line, I've taken the differential of both sides of the second line. Then on the fourth line, I've solved the third line for du. All I basically did was I brought du to the other side, multiplied with -1. Then on the next line, I've replaced dg with v dp minus s dt plus mu dn. Because remember, we just showed that if we allow the pressure to change, the particle number change, and the entropy to change, then the change in Gibbs free energy is v dp minus s dt plus mu dn. Cancel the terms to get the final result. du equals T ds minus P dv plus mu dn. This is the fundamental equation of thermodynamics.